Students, please tell me whether my screen is visible to you or not. Anyone, please reply me. Shall I start? Anyone? Hello, students. Students, please tell me whether my screen is visible or not. Okay, fine. So in our last class, we have seen the different types of flows, whether and the combination of flows in expansion. That means a combination of shock waves and expansion waves, or a supersonic body, or over a wedge-shaped body, and also a flat plate. And we have seen some formulas regarding that also. Just remember those formulas, because that is very important for you, because they may ask the formulas only. Okay, so now we are going to see two equations. One is the linear velocity potential equation, and another one is the Ackert's equation. In our last class itself, we have seen some beta term called beta. I have shown you some formulas. In that formulas, we have that beta. That beta comes from this velocity potential and Ackert's theory only. I will tell you what is that beta. And now see here, no need of this big derivation formulas only, but we should know what is a perturbation. Actually, normally for an incompressible flow and a compressible flow, there is a lot of difference. Even for an incompressible flow, we may consider some flow or some uniform flow or a airfoil. Means here we can see there is a uniform flow or an airfoil. When we pick some point over the surface of the flows or the airfoil, we can say this is the point which we are picking. And now when we see the relative velocity over that flow, we can see there are some small increment in its velocity because of the perturbation. The increment in velocity over this flow is called the perturbation. Normally we will say, see, this is a you can say this is the free stream velocity. Means the free stream velocity will we can it has x velocity and y velocity also. Normally when it is in horizontal axis direction, in this direction, then we may say the vy is equal to 0, and it only has vx. Okay, but when the flow is splitted over the airfoil, we can here the velocity will be like this. It will be inclined, so it may have two types of velocities. One is the component will be splitted into two halves. One is vx and another one is Vy, or we can say this is u and here it is v. Okay, so when consider here the velocity is v equal to 5 meter per second. Suppose over the airfoil, definitely there will be some change in velocities, because here the velocity will be at 6 meter per second, okay, or 5.5 meter per second. There's a, we know there will be some, there is a change in velocity. This change in velocity will be has happened because of the increment in the velocity, that because of perturbation. So the small increment in velocities is called the perturbation. Okay, so based upon that we will be solving some set of equation, and we found a velocity potential equation, like that is called linearized velocity potential. Same way for supersonic flow also we will be having some perturbation potentials. So that means there also the some increment in velocity will be there, and we will derive some equations for that, but no need of that equations and derivations and all, only we need the equations alone. Okay, so here the velocity potential they are considering the term as pi. This we have learned in the aerodynamics 1 in the starting itself. So for a two-dimensional irrotational isentropic steady flow of a compressible fluid, the velocity potential is 1 minus 1 by a square of dou pi by dou x the whole square into dou square pi by dou x square plus 1 minus 1 by a square into dou pi by dou y the whole square into dou square y by dou square pi by dou y square minus 2 by a 2 by a square dou pi by dou x into dou pi by dou y into dou square pi by dou x dou y, that is equal to 0. Then for a the velocity potential equation for slender bodies at low angle of attack, we will be finding the equations like 1 minus m infinity square into dou square pi by dou x square plus dou square pi by dou y square equal to 0. Okay, so this is the linearized velocity potential equation that we will be using. This term 1 minus m infinity square only we are considering it as beta. Okay, so normally we will be writing like m infinity square minus 1 as beta, because from Ackert's theory that you won't see here, but I will just mention that Ackert's theory also here. Okay, so one more condition, this see, for there is a difference in incompressible and compressible flows, right? So there will be some sort of we can't say, because normally why aerodynamics 2 or compressible flow studies come into picture means uh, in olden days when scientists or researchers when they invented the supersonic aircrafts and all, there they lot of difficulties come in the when for their designing and also flying the aircraft, because of the effect of the shock waves over the surface of the body. So because of the shock waves there will be some drag also, they faced some lot of difficulties. Okay, so that's why they, and a lot of accidents also happen because of the compressible flow effects, compressibility effects. So that's why the study over compressible flows mainly comes into picture, and they found that flow, incompressible flow and compressible flows are very different, and because of the shock or because of the compressibility, lot of things may change while flying an aircraft in supersonic flows and all. Okay, so that's why this compressibility correction factors and all will be having the compressibility correction factor, and even for finding the CP value also, uh, incompressible flow we have a CP formula, and for a compressible flow their CP formula may differ. Okay, that's why we are studying here. So here this linearized velocity potential equation, it is or the small perturbation potential, it is used for thin bodies and at a small angle of attack, and here both subsonic and supersonic Mach numbers will be used. Okay, it is valid for subsonic and supersonic flows. Okay, so here we can see the Cp for this Cp is equal to, normally for incompressible flow, Cp equal to what? P minus P infinity divided by Q infinity. Okay, P minus P infinity divided by Q infinity. But here for by considering this linearized velocity potential, there may be some changes for compressible flows and all. So therefore the Cp value will be like this: Cp equal to 2 divided by gamma m infinity square into P by P infinity minus 1. So normally generally we can say that Cp equal to minus 2 u bar divided by V infinity. This is the velocity potential because of the small perturbation. So this is the coefficient of pressure for small perturbation velocity potential equation. Okay, Cp equal to minus 2 u bar divided by V infinity. Just note down this two formula and this velocity potential formula also. Just write this three formulas and just intimate me when you finished. Actually how it came means, see here Cp equal to P minus P infinity divided by Q infinity. We know Q infinity equal to, what is Q infinity? Q infinity equal to half rho infinity V infinity square. Okay, half rho infinity V infinity square. So here we can multiply and divide by gamma P infinity. Okay, so half into gamma P infinity divided by gamma P infinity into rho infinity V infinity square. Okay, rho infinity V infinity. By cancelling it, we will get the half rho infinity V infinity square. Okay, so this we can write like this: gamma P infinity divided by 2 into rho infinity by gamma P infinity into V infinity square. We know A square equal to, what is A square? A square equal to gamma P by gamma into P by rho. Gamma P by rho. By substituting here, we will get that is equal to gamma P infinity divided by 2 into V square, V infinity square divided by this A square. This we can write like A infinity square also, or A square, whatever maybe. We know V square by A square equal to M square. So that is equal to, just I will write here, that is equal to gamma P infinity divided by 2 into M infinity, yes, into M infinity square. Okay, this is Q infinity. Okay, so Q infinity equal to gamma P infinity divided by 2 into M infinity square. But we know the formula for Cp is P minus P infinity divided by Q infinity. By substituting here, we will get like this: Cp equal to P minus P infinity divided by gamma P infinity divided by 2 into M infinity square. Okay, so we can write like this. The equation becomes, by taking P infinity outside, we will get the equation like 2 divided by gamma M infinity square into P minus, here we have, by taking the P infinity common, we will get here also P infinity will come in the denominator also, we have on P infinity. So P infinity will get cancelled. Therefore P by P infinity minus 1 into gamma into 2 divided by gamma M infinity square. Okay, then for then this equation it will comes after some simplifications and all, but no need of that and all. Just remember the formulas and all. Have you noted this formula? These two formulas. This two formula. Shall I change? Okay. Just away I told that this compressible flows and incompressible flows have different CP values, and also if the CP values change, automatically we'll be having different CL values also, and also different CM values also. Okay, so the automatically CL and the CM also, the moment coefficients also change because of the difference in this incompressible and compressible flows. Normally here we are according to this Prandle Glaurat rule, due to the compressibility factor, we have this beta equal to square root of, this from this beta equal to square root of 1 minus m infinity square. From this velocity potential equation, 1 minus m infinity square into dou square pi by dou x square plus dou square pi by dou y square equal to 0. From this we have the we are taking this 1 minus m infinity square as beta square. Okay, so therefore the compressibility equation, it will be come like this, or this velocity potential equation, it will come like this: beta square into dou square pi by dou x square plus dou square pi by dou y square equal to 0. No need of that and all. But from this Prandle Glaurat rule, what we are concluding is the coefficient of pressure is equal to Cp equal to Cpo divided by beta. Same way, this Cpo is the coefficient of pressure for incompressible flow. So there is a change in. Now you may understand this thing, because the coefficient of pressure for compressible flow. This is for compressible flows. Okay, this is for compressible flow. So there is a difference in coefficient of pressure for incompressible flow and compressible flow. When we compare it, we will get like the difference is 1 by beta of Cpo. Okay, Cpo is for incompressible flow. Cpo is for incompressible flow. So normally the based upon the compressibility correction factor, we will get the Cp for compressible flow as 1 by beta into Cp of Cp naught. Okay, so 1 by beta we know that is equal to square root of 1 minus m infinity square. Same way, Cl is equal to Clo divided by beta. Cl equal to Cl naught divided by beta, and Cm equal to Cm naught divided by beta. Okay, so for beta we are writing like square root of 1 minus m infinity square, and Cm also Cmo divided by square root of 1 minus m infinity square. Okay, just note this formula. We can move on to the next sum. Just a minute. Sivaraman, hello. சொல்லுப்பா. என்னது? ஆமா ஆமா. ஓகே, சரி. அதான் எனக்கு போட்டோ எடுத்து அனுப்புறீங்களா? இப்போ ஒர்க்கிங் வந்து ஒன்று வீடியோ எடுத்து அனுப்புறீங்களா? ஓகே ஓகே, முடிச்சுட்டு எனக்கு வீடியோவும் போட்டோ எடுத்துட்டு அனுப்புங்க. சரியா? ஓகேடா. ஓகே. ஆமா, ஆக்சுவலி எனக்கு அதுல இருந்து மேல போடும். ஆமா. ஓகே, ஓகே, ஃபைன். பை. Sorry students. Have you note down? Students, can you able to hear me? Hello? Anyone please reply me?
Yes, yes, sir. Yes, sir.
Okay, okay, fine.
Okay.
So once you
But
finish, just
can't
tell
see
me.
presentation is not visible.
Presentation is not visible. Okay, okay. I will.
Okay, I will.
Is it okay now?
Yes, sir.
Okay, fine. So have you noted down this formula? These four formulas? Students? Hello? Anyone?
Sir.
Finished?
Yes, sir. Yes, sir.
Okay. So here we have a sum like at a given point on the surface of the airfoil, the pressure coefficient is minus 0.3 at very low speeds. If the free stream Mach number is 0.6, calculate Cp at this point. Anyone know how to solve this sum?
So they had given CP incompressible. So by using CP is equal to CP not by root over 1 minus m square.
Yes. We can substitute like the formula is Cp equal to Cp naught divided by square root of 1 minus m infinity square. Okay. So they have given the free stream Mach number as 0.6. So for this we can substitute like 0.6 and the pressure coefficient at very low speeds. So that is minus 0.3. Just calculate it and find the answer.
minus 0.375, sir.
Minus 0.37. So this is the correct answer. Okay. So next one we have the theoretical lift coefficient for a thin symmetrical airfoil in an incompressible flow is CL equal to 2 pi alpha. Calculate the lift coefficient for M infinity, that is equal to 0.7. So we need to find the lift coefficient for the Mach number 0.7. Okay. How can we calculate this? Any idea?
Same procedure. In place of CP, we have to substitute
Yes,
CL.
same procedure. Just substitute and solve this sum. I can write the formula. CL equal to CLO divided by square root of 1 minus M infinity square. Okay. For in place of M infinity, we need to put 0.7, and in place of CLO, we need to substitute that 2 pi alpha. Okay. So that we will get one value for the CL.
So 8.8 alpha, sir.
8.8
alpha.
Others also got the same. 8.8 alpha is the correct answer. So here we have another one thing. For a free stream Mach number of 0.7, the critical pressure coefficient is minus 0.78. If the minimum pressure coefficient for a given airfoil is in incompressible flow is minus 0.6, then the flow over the airfoil at a free stream Mach number is Mach number of 0.7 is whether it is subsonic and compressible, completely supersonic, incompressible, and last one partly subsonic and partly supersonic. Please just guess the answer. What will be the correct answer?
So partially subsonic and partially supersonic.
How it is partially subsonic and partially supersonic?
Like they are given critical pressure coefficient. That means at somewhere of the wing, the Mach number at subsonic will turn into supersonic.
Yes. And also we can see the free stream Mach number is also 0.7.
0.7. I mean that
that means somewhere over the airfoil there will be Mach number equal to 1. Okay. And also they have given the critical term. If critical comes into picture, then there will be some point at the Mach number will be equal to 1. Okay.
Behind that location there will be supersonic.
Supersonic, and before that it will be subsonic only.
Yes.
So therefore the answer will be partly subsonic and partly supersonic. Okay. Okay. Next one, here we have a supersonic flow over a two-dimensional body with an attached oblique shock. An increase in free stream Mach number will cause oblique shock to move closer to the body, move away from the body, detached from the body, become a normal shock. Please tell me the answer for this. Anyone? So here we have a oblique shock, and the flow is supersonic only. An increase in Mach number, increase in the free stream Mach number means Mach number is keep on increasing, and will cause oblique shock to move closer to the body only. Okay, it won't get detached, because if it is detached means automatically it will become a bow shock. But here the shock is oblique shock only, so somehow it won't be detached and supersonic. Then became a normal shock. It won't become a normal shock, because after detaching only uh, the shock will be normal shock at the center, and afterwards it will be super, or it is a curved shock. Okay, then it won't move away, because since the Mach number is increasing, automatically we will be getting the shock will be closer to the body only. Okay, so the answer is move closer to the body. So this question, after we finish the thing, we will solve this question. Okay. So okay, we can move on to this topic, and afterwards we can move on to the sum. So next thing is the critical Mach number. Okay. So anyone, please tell me what is critical Mach number. You guys itself, we can easily tell the answer, because recently we have solved on some regarding this thing only, this critical Mach number only. So
I mean,
here,
when free stream Mach number turns to 1 at the point where on a wing, then the Mach number is termed as critical Mach number.
okay. So why we are thinking that transonic flow is a difficult flow to understand, or a transonic region is a difficult region to predict, or the theories which we studied for this linear potential and all, it is not valid for this, it is not correct for this transonic flow alone. Any guess? Because of this critical Mach number only, and because of the drag divergence Mach number, because of the rise in drag due to the shock formation over the surface of the airfoil. Okay, and because of the formation of the shock over the surface of the airfoil, we will be having separated flow after the shock, and this will cause a lot change in our drag and lift effect, that means aerodynamic performance and all. Okay, so here we have four diagrams, four different airfoils, and the Mach number, or the free stream Mach number, is changing from one airfoil over the other airfoil. So we are picking a point over here. That means when the Mach number is 0.3, somewhere over the airfoil, as we discussed in our problem itself, over the airfoil, the, or a problem, not in the problem, or in the our linearized velocity potential, the free stream Mach number will change because of some increment in velocities. That means because of the small perturbation potential over the surface of the airfoil and all, the flow over the surface of the airfoil. Okay, so somehow over the surface the velocity will be increased. So we are picking a point here. In this point, we can say, you can see here, the local Mach number over this point is 0.435 when the Mach number is, free stream Mach number is 0.3. When the free stream Mach number is increased to 0.5, same at the point A, the Mach number is 0.772. But when the Mach number increases to 0.6 and all, automatically over some point the local Mach number is increased to 1. When this when the local Mach number increases to 1, then that point is called the, or that Mach number will be called as the critical Mach number. Okay, so after if you are increasing the flow over this critical Mach number, so here the Mach number over here is the critical Mach number. Okay, when we are increasing the free stream Mach number above this critical Mach number, we will be having shock over here. That means we will be having shock here and here. The point, the separation here is the sonic line, And here we have this so because of the shock over the surface of the airfoil, we will be having the separated flow here. Okay, we will be having the flow separation here. This will cause the tremendous increase in drag. That's why in transonic flows, this linearized velocity potential or the compressibility correction factors and all, this won't this is not suitable for this transonic flows alone. Okay, so here for CPA, we know the CPA is 2 by gamma m infinity square. This and all we have already I have told you about this CP for this incompressible flows, sorry, compressible flows. That is CP equal to 2 by gamma m infinity PA by P infinity minus 1. When over the airfoil at some of the local point, local Mach number, when it reaches 1, that means m reaches 1, the critical the coefficient of pressure will become critical coefficient of pressure. So here we have the critical we have the formula for this. CPA equal to 2 divided by gamma m infinity square into 1 plus gamma minus 1 divided by 2 into m infinity divided by 1 plus gamma minus 1 divided by 2 into ma square. Ma is the local Mach number. When this local Mach number reaches 1, we will be getting the critical pressure over the airfoil. That means when substituting this ma equal to 1, we will be getting the critical coefficient of pressure. That is CPCR equal to 2 divided by gamma into m critical square into 1 plus gamma minus 1 divided by 2 into m CR square divided by 1 plus gamma minus 1 divided by 2 into whole power gamma by gamma minus 1 minus 1. So this equation, it comes because of the pressure ratios. That is you all know, studied this P divided by P naught, P divided by P naught, then rho divided by rho naught formula and all. By substituting the formula, we will be getting the coefficient of pressure over the local point over the surface of the airfoil as CPA equal to 2 divided by this formula we will get. When critical pressure is reached or the critical Mach number is reached, we know the local Mach number will become 1, so that we can straight away substitute the value of local Mach number as 1, and we will be getting the formula for critical pressure over the airfoil as CPCR equal to 2 divided by gamma m critical square into 1 plus gamma minus 1 divided by 2 into m CR square divided by 1 plus gamma minus 1 divided by 2 into whole power gamma by gamma minus 1 minus 1. Okay, so here they have plotted the value for this Mach m infinity, that means the Mach number and the CP. Okay, for when the Mach number is increasing, we'll be having the, for a thin airfoil and a thick airfoil. For thin airfoil, the MCR is that means here we have one thing like, see, I have a question for you. So here we can see here the critical Mach number is 0.6. When when the Mach number is 0.6, that means the free stream Mach number is 0.6. Somewhere over the airfoil there will be 0.1. That means Mach number will be equal to 1. So after that, shock will be formed. So when we increase the critical Mach number, shock will be formed over the airfoil. But the critical Mach number what we have here is 0.65. Okay, so whether we need larger critical Mach number or lesser critical Mach number, that means my question is if m equal to 0.6 is good for an airfoil, for an aerodynamic performance of airfoil, or m equal to 0.8 is good for an aerodynamic performance for an airfoil, whether this is good or this is good. Anybody? Do you know why supersonic aircrafts are designed with thin airfoils? Guys?
So because even for low Mach numbers, the critical Mach number, I mean, they can easily, if thick aerofoils will achieve, I mean, they can achieve critical Mach numbers on wing itself.
Actually,
Actually,
for supersonic flows and
for
all,
supersonic flows
or supersonic airfoils,
or
why they are
supersonic
designed for
airfoils, we are designed for
thin airfoils means if you are getting
if you are getting
at see here Mach number is 0.6,
Mach number is
free stream
0.6,
Mach number is
Mach
0.6
number is
means
0.6
somewhere over
means
the airfoil supersonic
power over
flows
the
will be
airfoil
reached, and
supersonic flows will
because
be
of
reached,
that
and because of that
automatically drag is increasing.
automatically
Okay,
the drag is in. Okay. Yes, sir.
because of that factor
Because
only they are considering they want a thin airfoil so that the Mach number will be we will be getting the critical Mach number via as a larger critical Mach number. That means m, if the m is 0.8 means we are getting the critical Mach number as 0.8 means then that is good for an airfoil. Okay, otherwise we will be getting the drag divergence Mach number will come will come into picture, so that we will be getting large amount of drag over the airfoil due to the separation of flows. Okay, that means flow will be like this. Somewhere it will be sonic. After sonic we will be getting this large amount of flow separation, okay, behind the airfoil. So if we are extending the critical Mach number means, if you are getting a larger critical Mach number means automatically some the shock over the airfoil will be like this, so that over the trailing edge region only we will be getting some amount of separation that won't affect the flow of an airfoil. Okay, for that purpose only we are designing supercritical airfoils for supercritical airfoils for what to say passenger aircraft, which the speed of the aircraft is zero point 0.8 or something and all. Okay, high subsonic airplanes are there now. For that airplanes and all we are using this supercritical airfoils. Do you know how the supercritical airfoil is? Here also same concept only. When we are here the CD is plotted for drag divergence Mach number is sorry, coefficient of drag is plotted for m infinity. Okay, so here also, as I told earlier itself, if we have less critical Mach number, we will be getting more amount of drag because of this drag divergence. That means here we can see the Mach number is the coefficient of drag is constant over some point when up to the critical Mach number. Okay, after this critical Mach number reach, there is a small increment in drag. So the drag is rising up to some point. After some point the drag is rising at a tremendous level, drastically it is rising to some point. So over this region is called the this point, the Mach number is called drag divergence Mach number. After that it will be the divergence, that means the drag will be increased in a tremendous manner. Okay, that's why for that purpose only Whitcomb he designed the shape of the aircraft for supersonic flights and all. like bottle shaped aircraft. That is why transonic area rule comes into picture for reducing this drag divergence Mach number. They are designing the shape of the supersonic aircrafts like this. Okay, in this form, like they will design. I will show you one. Okay, that I will show. That's why the supersonic aircraft shape will be like a bottle shape. Okay, Coke bottle shapes and all. Okay, so for this purpose only, we are using this supercritical airfoil also for high speed transonic aircrafts and all, so that it may have a flat surface over the top side and a round shaped nose and a cusped trailing edge. Okay, the shape of the supercritical airfoil is like this. It may have a flat surface and a leading edge. Shape of the leading edge is a round shape, and trailing edge, it will have a cusped trailing edge. Okay, so that this type of airfoils, it will increase the critical Mach number. Therefore we can reduce the drag divergence Mach number also. Okay, so here next one is the transonic area rule. So if you are using the area rule which was prescribed by this Whitcomb, we will be getting the less drag, and without area rule the drag is more for supersonic aircrafts and all. We can see here, olden days the aircraft shape will be like this. Over the here the wing, here we have the wing like this. The wing is like this, means the cross section of the airfoil shape will be like this. It will be like this only. Okay, but afterwards, because of this shape, we are getting more drag. Because of the drag divergence Mach number, we will be getting more drag. So what Whitcomb did means, he designed on shape of the wing with a cusped shape in the near this, like this, like a bottle shape, and he tested in the wind tunnel, and he found that with the, if you are using the area rule, that means a bottle shaped aircraft, or in the shape of the aircraft will is producing less drag. Okay, that's why we are preferring this type of fuselage for supersonic aircrafts and all. These things and all come after this world war only. Okay, so here we have the supercritical airfoils. Normal airfoil, if you are using the thick airfoils and all, you will be getting the over some point the drag will be like this. Sorry, shock will be formed like this, so that after that we will be having separations. Because of this separation only, we are getting the large amount of drag. So if you are using the supercritical airfoil, means we will be having a flat surface over the surface of the airfoil, top surface of the airfoil, and we are having a cusped trailing edge. And because of this shape, we will be having, or the sonic point will be reached, or the critical point will be reached, or the local Mach number will reach 1, be reaching sonic flow at this point only, at near the trailing edge only. So this may reduce the drag of the airfoil. Okay, so normally supercritical airfoil has certain characteristics. It may have a large leading edge radius, and a flat upper surface, rounded lower surface with the maximum thickness location at almost at a 50%, and may have a cusped trailing edge, and here the flat or even negative camber in the forward section, and high positive camber in the rear section. Okay, so just note on this characteristics: large leading edge radius, comparably flat upper surface, rounded lower surface with a maximum thickness location at 50%. At the half of the airfoil, it will be having the maximum thickness location, and flat or negative, even negative camber will be at the forward section of the airfoil, and over the trailing edge section or rear section will be having a high positive camber. Okay, noted. So this is an gate question only. The geometrical feature of a supercritical airfoil are, anyone? Anyone, please tell me what is the answer for this? See here, already I told you for a supercritical airfoil, we will be having we won't have a sharp leading edge. So these two answers are wrong, and so the remaining answers will be from A and C only. Okay, and also here we have rounded leading edge. So here a supercritical airfoil have rounded leading edge only, but it don't have a curved upper surface, so that it also, this thing also it won't come. This is wrong, B is wrong, C is wrong, D is wrong, so that the answer is rounded leading edge, flat upper surface and high camber at the rear. Okay, rounded leading edge, flat upper surface and high camber at the rear. The answer is A. Okay, see, just note this sum and try to solve this sum. Okay, I will share you the PPT so that you can note from that. Or okay, I will share it now. Please tell me the answer for this. An oblique shock with a wave angle beta is generated from a wedge angle theta. The ratio of Mach number downstream of the shock to its normal component is sin beta minus theta, cos beta minus theta, sin beta plus theta, cos beta plus theta. Anyone? Please tell the answer.
So it would be sin beta minus theta.
Others? Because we know the downstream Mach number m2 equal to mn2 divided by sin beta minus theta. So the answer is beta minus theta only. Okay. So okay. Just note the sum and solve the sum by your tomorrow's class. Make this as an assignment for you. So just look at the sum. Here we have a problem like calculate the lift and drag coefficient for a flat plate at 5-degree angle of attack at Mach 3. So for this type, just for your understanding purpose only, I have just solved the sum here, because they won't ask this type of sums, because we are for this and all we need gas tables. Without gas tables we can't solve. Okay, because we need the pressure ratios and all. So first they have given a flat plate with the angle of attack of 5-degree. Okay, so theta will be 5-degree, and the Mach number m1 is 3. So m1 will be 3, v1 is so for this m1 we from gas table we can find this v1. Okay, for this 5-degree angle, and also for this Mach number we can find the V1 as, that is here we have the expansion wave over the top surface. So straight away we can find the V1 as from the gas table as 49.76. So after finding the value of this V1, we can substitute the value of V1 in this formula, that is V2 equal to V1 plus theta. So V1 is 49.76, so that by substituting it we will get V2 equal to 54.76. So from this gas table we can find for this expansion wave, for this expansion wave angle we can get the Mach number as M2 equal to 3.27. okay, because as I shown you earlier itself, there will be like a form for Mach number, the table will be like this: Mach number, expansion wave, and theta. So if you know the value of theta, we can straight away find the value of this expansion wave angle also, or if you know the value of this Mach number, we can straight away find the value for this expansion wave angle also. okay, so here also next what they have did is, for the initial Mach number M1, they found the pressure ratios like P01 by P1, and for this M2 they have found this P02 by P2. So the pressure ratios for this is, for P2 by P1 equal to, because P2 by P1 equal to P01 by P1 divided by P02 by P2. okay, by substituting the value we will get the static pressure ratios like 0.663. okay, so for this M equal to 3 and theta equal to 5, we have the beta as 23.1. okay, so we know this Mn1 formula equal to M1 into sine beta. So that is equal to, this is from oblique shock, because here we have this oblique shock. Here also Mach number is coming from M1 only. okay, so downside it is oblique shock, so that with this formula we can in oblique shock we can find the value for beta. After finding that, we can substitute here and find the value for Mn1. The value will be 1.177. with this Mn1 we can find the pressure ratios there for Mn1 for this Mach number, that will be 1.458. okay, so now we can substitute the formula, like, because they asked us to find the lift and drag coefficient for this. So the lift formula is L dash equal to P3 by minus P2 into C cos alpha. okay, so by substituting here we know CL equal to L divided by Q infinity into S. So for Q infinity we have found that formula, that is gamma by 2 into this formula already we have found from for CP and all. okay, for Q infinity we found here we can see, I will show you. Sorry, I have in your lecture video you can find that formula. okay, so by substituting the formula for Q infinity, the equation becomes like this, that is 2 divided by gamma m1 square into P3 by P1 minus P2 by P1 into cos alpha. So we know the value for alpha, we know the value for P3 by P1 and also P2 by P1 and also the initial Mach number. So by substituting we can get the value for CL. Same way, by substituting the Q infinity value, we can find also this CD also, because we know P3 by P1 also we know, P2 by P1 also know. Sin alpha, we can substitute the value of alpha and we can straight away find the value for CD. This is how we can find the value for CL and CD. okay, just I will share you the PPT. So, and I have given on some assignment, just try to solve that sum. okay, so we can wind up here. Students, you can leave now. I will tell you when the next class is. Okay, and I will share you the PPT in your WhatsApp group so that you can assess the PPT and try to solve those sums and try to note down the formulas what I have shown in your PPT and all. Okay, now we can leave.